Hi there, and welcome to our sixth lecture on our course on photonic device. On today's lecture, we're going to keep on talking about the density of states, and we're going to find an expression for the density of states as a function of the magnitude of the wave vector k. Just as a reminder, we saw on our last lecture that we were able to define a k space or a wave vector space, just like our three-dimensional space, which is the space that contains all wave vector values. So for example, we could, in Cartesian coordinates, we could have kx, ky, and kz, and any vector in the k space or the wave vector space could be defined as a superposition of the scaled version of these three vectors. And we also saw that kx, ky, and kz were only able to assume discrete values which were separated by pi over lx, ly, and lz in the respective direction. So, as a reminder, Lx, Ly, and Lz are the dimensions of the three-dimensional solid that we are considering. So, for example, this could be Lx, Ly, and Lz, the dimensions of the piece of semiconductor, and the wave vector k is related to the momentum of the electron inside this solid, and the k values that it could assume are discretized, and the distance between points along any of these directions is pi over Lx, Ly, or Lz. In this direction, for example, it would be Ly, here pi over Lx, and here pi over Lz. So Lx, Ly, and Lz are the x, y, and z dimensions of the solid, okay, of the piece of semiconductor, and also m, n, and p are integers. So in these expressions, m, n, and p are integers, so that the points along each direction are spaced by pi over the dimension. Also, to each value of discretized k vector corresponds an also discretized energy value. This can be seen in the EK diagram, or the band structure, where you have E on the y-axis and K on the x-axis, and the bands describe the energy and wave vector values that correspond to the states which the electrons can assume. So this is the block or the piece of semiconductor centered at the origin with dimensions Lx, Ly, and Lz, which we use to derive the discretization of the three directions, kx, ky, and kz. And we also saw that you could have as many as 10 to the 7 to 10 to the 10th points in any given direction in the k space. So if the distance between points in the x, y, and z, or kx, ky, and kz directions are respectively pi over Lx, pi over Ly, and pi over Lz, you could define a cube, or more precisely a rectangular cuboid with minimal dimensions in the k space, and we'll see why this is important in a minute. But so what we're doing here is we're defining a rectangular cuboid with minimal dimensions. So let's imagine that you have a cuboid in k space like so, and the dimensions, because in the y direction the points are separated by pi over Ly, are pi over Ly in this direction, pi over Lx in this direction, and in the z direction it's pi over Lz. Okay, so you have this cuboid, which is the smallest cuboid that you can define in this space given this discretization. And we can readily find the volume of this by multiplying the length of the three sides. So why is this volume important? Well, it's important because if the distance between points in the k space, in the wave vector space, is pi over Lx in the kx direction, pi over Ly in the ky direction, and pi over Lz in the kz direction, then you can think of each state in each discrete point in the k space as occupying a volume exactly equal to the volume we just defined. So think about this a little bit. So we're going to use this volume later, and the volume occupied by one state, by each point, right, by any point that you defined in the wave vector space, for example, this point right here, the volume it occupies is equal to the volume of this cube with minimal dimensions, okay? Because the spacing between points is what we just said. So this volume, like we said, is going to be derived by multiplying each of the three dimensions. So pi over Lx times pi over Ly times pi over Lz, which is equal to pi cubed divided by the volume of the solid. Okay, so this is the Lx times Ly times Lz is the volume of the solid in real space, in our three-dimensional real space. So what we just defined is the volume of each state, the volume of one state. And this is going to be used in order to define or to determine the expression for the density of states. So what we want to find here is the density of states, rho, ultimately rho of E, but first we're going to find rho of K. Okay, then after that, in our next class, we're going to find rho as a function of E from rho as a function of K, which we'll find right now. Well, by the definition of the density of states, you could define it as a function of K or as a function of E. In either case, it was defined in such a way that the number of points the number of points with wave vectors between k and k plus a differential dk is equal to rho of k dk, right? So if you want to find the carrier concentration in the conduction band, we said that you need to integrate this quantity. So rho of k dk over the entire conduction band. So you would define the initial k here and the final k here to correspond to the initial and final k's in the conduction band. But this is how we define rho of k, and rho of E, if you replace k by E in these expressions, is defined in the same manner. The reason for this is that rho of k is the number of available states or states available per unit k with wave vector of magnitude k. So what we're saying here is that rho of k, right, is the number of available states per unit k. So it's something like the number of states dk, the derivative of the number of states with respect to k at k, at a wave vector value equal to k. So because of this, right, it only makes sense that if you replace this here, you will find the total number of states at a wave vector value of k, and if you integrate it over a certain range, you'll find the number of states in that range, within that range of k values, okay? So this is mainly the reason, but let's focus on the fact that the number of points with wave vector k's between k and k plus dk is equal to this quantity here. This is what's important. So if you find the number of points that have k's between k and k plus dk, you have this, okay? So this is what is the key concept here. If we want to find this, because we want to find rho, we can find the number of points with k's between k and k plus dk, okay? So how can we do this? So if we find the volume in K space, the volume of the region between K and K plus dk, the volume of the region corresponding to wave vectors values between K and K plus dk, and then we divide this by the volume occupied by each state, as we just said, is this right here, right? It has to make sense that this will give us the number of states, the number of points within this region, okay, that correspond to wave vectors in this range, okay? So this will give us this. To do this, we're going to consider that K, without the bold type here, is the absolute value of the wave vector K. Okay, we could denote this in this way, but we're considering the magnitude or the absolute value of the wave vector K. So perhaps it's easier to look at this if we look at the K space, the wave vector space. So where are located in this space the points that have wave vector with magnitude equal to K, right? Well, they're going to be exactly at the surface of a sphere with radius K. Okay, so let's say that this is vector K, so this magnitude here is K. If you define a sphere centered at the origin, the surface of this sphere is going to have points, they are located at the surface of the spheres, whose magnitude of the wave vector is exactly K. We are only concerned with the first octant, or the 1/8 of the sphere that is shown here, because we are only concerned with K's that are the absolute value or the magnitude of the wave vector K. Okay, so just the positive values. So positive value of Kx, Ky, and Kz. That's why we're only concerned with this first octant, or this 1/8 of the sphere. Now, if we define another sphere with a radius slightly larger, so that the radius is actually, instead of being just K, it's K plus dk, a differential dk, like this, you're going to have this outer sphere right here. And of course, the points at the surface of this outer sphere have wave vectors K plus dk. And all of the points in the volume that's located in between these two spheres, including the surface of the spheres, are the points with wave vector values between K and K plus dk. Okay, so this has to make sense. So if you take the volume of this shell right here, defined between these two surfaces, the surface of the inner sphere and the surface of the outer sphere, you have a shell of thickness dk. Okay, the thickness of the shell is dk, the differential dk, and this defines a volume, a shell in space, which is the volume occupied by all of the points with wave vectors between K and K plus dk. Okay, so this is the volume, the shell here with thickness dk is the region that has all of the points with wave vectors between K and K plus dk. So all of the points are going to be inside this shell right here. And well, if you think about it, if you divide the volume of this region, the volume of the shell with thickness dk, by the volume occupied by each state, you will find exactly the number of states within this range, right? The number of states that could fit inside the shell, which is the number of states with wave vectors ranging between K and K plus dk. And since we said that the number of states with wave vectors with K's between K and K plus dk is, right, we said it right here, is equal to this quantity right here, then we'll be, we'll indirectly be finding this quantity, which is rho of K dk.